Hello everyone from Math 2200, Discrete Mathematics. It's Professor Wenson here again with a video on your ZyBooks Section 4.1 titled The Definition of Functions. So here it is, and I'm going to be reading a lot of this to you. It's kind of like the beginning of every chapter. All of Chapter 4 is on the things called functions, and you've heard the word function before, I'm sure, in your mathematical studies. We're just getting into a more definition related to the Cartesian product of two sets, which you saw in Chapter 3. So a function maps elements from one set, say x, to elements of another set, say y. Many functions are mathematical functions that map numbers to numbers, such as the function x squared, which maps a number to its square. Discrete mathematics is often concerned with functions that map between other kinds of sets, such as binary strings or a set of tasks. Thus, an assignment of people to teams, or of guests to hotel rooms, are also examples of functions. A function from set x to set y can be viewed as a subset of their Cartesian product, x cross y. Right, so basically any ordered pair, x comma y, belongs to the function f, right, a subset of the Cartesian product of x and y, if f maps x to y, or f assigns element x from the first set to element y from the second set. It is possible that x and y are in fact the same set, in which case f is a subset of x cross x, or remember we wrote that as x to this with a little 2 on it, when you had the Cartesian product of a set with itself. Alright, so definitions here. Lots of definitions, and you notice all the bold words showing up. Alright, so a definition of a function. You've already kind of seen it up here in the first paragraph. A function, usually going to be denoted by a lowercase letter. It doesn't have to be, but a function, f, that maps elements of a set x to elements of a set y is a subset of the Cartesian product of x and y, right, x cross y, such that for every x in x, for every little x, for every element in the set x, there is exactly one element y in set y for which, the ordered pair x, y belongs to function f, or that such that x maps to y, or x is assigned to y. So every single element of set x is assigned, is mapped to exactly one element from set y. Now some notation. You'll see the name of the function, like a lowercase f there, colon, and then this arrow notation. We have set x, arrow, set y. This means I have a function where it takes elements from set x and maps them to elements from set y. Okay, this is the notation to express that f is a function from set x to set y. This first set in this notation, the set x, is called the domain of f. Right, it's like where all the inputs are coming from. And then this set over here that those inputs, those elements are getting mapped to, set y, is called the target of f, or the codomain of f. Right? So this set y, this set after the arrow, called the target or the codomain of f. Now the fact that f maps x to y, or the ordered pair x, y belongs to f, function f, can also be denoted as f of x equals y, and you've seen this notation, I'm sure, in some pre-calculus or algebra course. Function f assigns element x to element y, right? F of x equals y. Right. Now, remember the definition here is saying that it's a universal statement. Right? For every element of the domain, there is exactly one element of the target that it maps to. So if f maps an element of the domain to 0 elements, or more than one element of the target, then f is not satisfying this definition. F is not well defined. Okay, so again, by definition, every element of the domain has to map to exactly one element of the target, or the codomain. And if that's not happening, then our mapping or function is not well defined. If f is a function mapping x to y, and x is a finite set, then the function f can be specified by listing the pairs, the ordered pairs, x comma y, where x maps to y in f. You can actually, if the domain is a finite set, then you can actually list the set of all the ordered pairs in the function, right, if it's a small enough set. Alternatively, a function with a finite domain can be expressed graphically as an arrow diagram, which again you've probably seen. In an arrow diagram for a function f, the elements of the domain x are listed on the left, and the elements of the target y are listed on the right. Then, there is an arrow from an element of x to an element of y if and only if that ordered pair belongs to the function, if x actually maps to y. And since f is a function, every element in the domain x has exactly one element in the target, y, such that x comma y is an ordered pair in the function. Which means that in the arrow diagram for a function, there is exactly one arrow pointing out of every element in the domain. All right, so they go through, here's an example of a function and an arrow diagram. You can play the animation here. I'm just going to point this stuff out. So you see this function called f that goes from set x, takes elements of set x and maps them to elements of another set called a. So the domain is called x, and the target or the codomain is called a. X has the elements w, x, y, and z. The target a has elements a, b, c, d. So you see the domain elements written on the left here, the target elements written on the right. And then here function f is listed as a set of ordered pairs, right? And every function that we're going to come across can be expressed as, a subset of the Cartesian product of the domain and target, right? So a set of ordered pairs. So you have w comma a, x comma a, y comma d, z comma c. Right, here is a subset of x cross a, the Cartesian product of x and a. So w maps to a, so you see here I have an arrow from w to a. And that's it, right? If this is truly a function, there should only be one arrow coming off of w. X maps to a, so I have one arrow coming off of x mapping to a, pointing to a. Y maps to d, so again one arrow only coming off of y going to d here, and z maps to c, so again exactly one arrow from this element z in the domain to this element c in the target. Okay, so now notice that not every element of the target needs to be hit. The elements of the target that are hit, right, the elements of the target that are mapped to, make up what's called the range of the function. So in this particular picture, and you see the word range at the bottom here in bold, we'll get to that in a second, but the range of this function would be the set A, C, and D, right? Just the elements that get mapped to. So B is not in the range. B is in the target, the codomain, but B is not in the range. It is not mapped to by the function. So that's what I got here, the definition of the range of a function. So for function, f mapping from elements of x to elements of y, domain x, codomain or target y, and element y is in the range of f if and only if there is an element in the domain that maps to it, right, such that x comma y is in the function. Expressed in set notation, the range of f is all the elements of y, all the elements y such that x comma y is in the function for some element in the domain x. Simple as that. So the range of f is a subset of the target, not necessarily equal to the target. Now the range could be the target, right? If every single element in the target is mapped to, then the range is equal to the target. But very often you're going to see that the range is a proper subset of the target, meaning there are going to be some elements in the target sometimes that are not mapped to, like in this picture up here, where B is in the target, but not in the range. All right, so look at this example here. Now, the title of this activity is, recognizing well-defined functions. I mentioned talking about well-defined earlier, when functions are satisfying the definition of a function or not. Look at what they did here. So they took this same function from this picture and they added an arrow off of y. They added an ordered pair, the ordered pair y comma b. So you see that purple arrow showing up, y to b. Well, now every single element in the target is mapped to, but this is no longer a well-defined function. Because remember, in a well-defined function, the definition of a function, every element in the domain goes to exactly one element of the target. Well, that works for w. W goes to just a. Works for x, right? X goes to just a. It works for z, right? Z goes to just c. But y is a problem. Y in the domain maps to D and B. Right? It maps to not exactly one, but two elements. So as it was saying earlier, if f maps an element of the domain to no elements of the target, or more than one element of the target, then f is not well defined. So this is not a function. See, they say that here. Okay, so pay attention. Hopefully you're able to recognize a well-defined function, especially from a set of ordered pairs or a mapping arrow or an arrow diagram like this. All right, so let's take a look at this example. So here we're given two arrow diagrams, right? One in red called F, and one in green called G. And the domain set is A, B, C, D for both of these. The target set has W, X, Y, and Z. The question first is F, this arrow diagram, this mapping, is F a function? So by definition, every element on the left, every element of the domain should map to exactly one element of the target. Right, the set on the right. So A maps to X, that's it. So far so good. But B maps to W and Y. It maps to more than just one element. So no, there is an unmapped element in the domain. Well, no. Every element in the domain maps somewhere. but an element in the domain is mapped to two different elements in the target, so that's why f is not a function. Is g a function? Yes. Right, see how a maps to z and that's it? B in the domain maps to z and that's it. C maps to w and that's it. And D maps to x and that's it. Every element on the left maps to exactly one element on the right. So yes, g is a function. Hopefully, again, that's easy to recognize when you have a well-defined function. Okay. Alright, so here I am going to draw this on a picture. I'm going to draw a mapping and arrow diagram because, again, my domain and target have finite number of elements, are finite. So it should be easy to, they're not that big either. So I'll start making a mapping, an arrow diagram here. Okay, so here are the sets in that activity. And set A has elements A, B, C, and D. Set X has elements 1, 2, 3, and 4. And we're looking at this function f, lowercase f, from mapping elements from A to elements from X. Again, the set A here is called the domain, right? It's where all the inputs are. This set here on the other side, what you're mapping to, is called the target, right? Or the codomain. Okay, same thing. And then look here. The function f is described to us as right now just a set of ordered pairs. And do you see that this set of ordered pairs is a subset of A cross X? All right, it's a subset of that Cartesian product where all these ordered pairs in here, the first elements coming from set A, the second coordinates or the second positions in these ordered pairs components are coming from set X. All right, well, here's an arrow diagram for this. Right, so over on the left, there are 4 elements. I'll do like 4 little dots. Right, here's for set A, and you got A, B, C, D. Very easy to make, I hope, these. And on the right side, the elements of set X. Again, there's only 4 of them, so just 4 dots. And the elements are 1, 2, 3, and 4. And here's set X. And if there's an ordered pair in this set little f, I'm going to draw an arrow representing that mapping in this picture. Okay, so we're seeing that A maps to 3, right? So A maps to 3, so I draw an arrow there. B maps to 1, arrow there. C maps to 4, arrow there. And D maps to 1, arrow there. Alright, so if you look at this, every single element in A, every element in the domain has exactly 1 arrow coming off of it. They map to exactly 1 element of the target. So f here is a well-defined function. Right? It satisfies the definition of a function. Right, so that's point number 1 I want to make. The next one, we know the target. Right, the target is X, the set with 1, 2, 3, and 4 in it. But what's the range? The range of f. Again, the range of f is simply all the elements that actually get mapped to in the target. So 1 gets mapped to, so 1 belongs to the range, right? 2 does not get mapped to, right? See, no arrows that go into 2. There's no ordered pairs where 2 is the second component. So 2 is not in the range of f. 3 gets mapped to, and then 4 gets mapped to as well. So the range of f is just the elements 1, 3, and 4. And again, the range of a function should be a subset of the target. Right, that was x, right? The range of a function will be a subset of the target. So it could be equal, but it could also not be equal like we're seeing here. And then some other notation. Remember the ordered pair A3, belongs to function f here. Another way to say that is to say that f of a equals 3, right? This function f maps a from the domain to 3 from the target. The ordered pair b comma 1 is in this function, and that means the same thing as saying that f of b is equal to 1. Okay, again, you've probably already seen this kind of function notation before in, like I said, a previous algebra or pre-calculus class. All right, so keeping all this in mind, going back here, what is the target of function f? They told us it's x, this set with 1, 2, 3, and 4. Again, that might be equal to the range if every element in the target is mapped to, but that's not the case here. All right, we saw just 1, 3, and 4 are mapped to, so that's the range of f. What is f of c, right? So that's just, what does f map c to? It maps it to 4, right? And which of the following sets could be a correct, well-defined function definition for a function called g that goes from x to a? So this switches it up, right? Function f up here is from a to x. So in the ordered pairs, you have an element from a first, comma, and then an element from x. This function g we're looking at is going to switch that up. So you should have elements from x first mapped to elements from a second. So so you see here, so not this one. This would be from a to x. This is from x to a, but look, 1 maps to a, 2 maps to d, 2 maps to b. You see 2 from the domain from x maps to 2 different elements from the target a. So this here is not a well-defined function. How about this? 1 maps to a, 3 maps to b, 4 maps to c. This is good so far, but remember the definition of a function. Every element of the domain maps to exactly one element of the target. What about 2? 1 maps to a, 3 maps to b, 4 maps to c. What does 2 map to? 2 doesn't map to anything. That's not exactly one element of the target. So this here, number 3, the third option, is not a well-defined function. But this one here, 1 maps to a, 2 maps to a, 3 maps to b, 4 maps to b. Every element of the domain x is mapping to exactly one element of the target a. This would be a well-defined function for g here. Okay, and then I'll let you do 5. All right. Now, very often, so far our examples here have had, finite domains and finite targets. But very often we're going to look at functions where the domain and the target are, infinite sets, like the real numbers or the integers or something. So a mathematical function f is often defined by describing how f acts on an input x. Right? As in, like from algebra, f of x equals x squared minus 2. This means f maps a number to its square minus 2, right? So it would map 0 to -2 or 5 to 23. You just describe how the domain value is mapped to the target value. However, the definition is not complete until the domain and the target of f are specified. So for example, function g here from the reals to the reals, where g of x equals the absolute value of x, right? This is a well-defined function here. You have a domain, you have a codomain or a target, and then here's a little rule describing how elements of the domain are mapped to elements of the target. You need all that stuff for a proper definition, a complete definition of a function. Okay, so again, note that G maps every real number to a real number, right? However, G does not map any number to a negative number, right? You know, this G here takes a real number and maps it to its absolute value, which will never be negative. Right? So that means that the range is not the same as the target, right? There are some elements in the target, like the negative numbers, that will never be mapped to by this rule. All right, so again, can you look at a rule? All right, can you look at a properly defined, can you look at a complete function rule and say whether or not it's well defined? And remember, to be well defined, I'm going to say it a lot. You've heard me say it a lot already. Every element of the domain is mapping to exactly one element of the target. No more, no less. So how about the following? Are the expressions below well-defined functions from the reals to the reals? So my domain and target are the real numbers. So how about this first rule? So I have a function f that takes a domain value x and does 1 divided by the quantity x minus 1. Is this a well-defined or not well-defined function? I'm going to pull this up on some paper and we'll explore it a bit. Okay, so here's the function that was mentioned. All right, again, f is from the reals to the reals, and f takes a number to 1 over that number minus 1. So again, these are infinite sets, but if you'd like, just to explore a bit, I can start making a little mapping where on the left side I have some real numbers, on the right side I got some real numbers. Now I'm just going to list the integers here, but you could put it's any real, pi, square root of 2, a half. So this is going to go on that way forever. There are infinitely many of these. All right, so say -3, -2, -1, 0, 1, 2, dot dot dot. And again, I could put like a half here, and, pi. It's the reals. Okay. Let's see where these would map. Okay, now again, you can list reals over here. I'm just going to list their outputs. So like, what would a half map to? F of a half would be 1 divided by a half minus 1 is -half, and then 1 divided by -half this would map to -2, right? And -3 would map to -1/4. I'm just doing this here. Again, impossible to list them all, right? There's infinitely many real numbers. So this is not a great idea, but it's just to explore some things. -2, right, would map to -1/3. -1 would map to -half. 0 would map to -1. 1 divided by 0 minus 1. 1 divided by -1 is -1. What about 1? What about 1? F of 1, according to this rule, would be 1 divided by 1 minus 1, or 1 divided by 0. Uh-oh. Can't divide by 0. Alright, so you gotta keep that stuff in mind, right? Remember all your algebra stuff. Can't divide by 0. No even roots of negative numbers in the reals. No logarithms of non-positive numbers. Stuff like that. So I mean 2 would map to something. 2 would map to 1. Pi would map to whatever 1 divided by pi minus 1 is. The problem here is the number 1. 1 doesn't map to anything. So the definition of a function is not satisfied. Remember, the definition is every element of the domain maps to one value of the target. Every single one. I just found one that doesn't map to anything. So because of this number 1, this element 1 in the domain, this is not a well-defined function. I'll leave this one for you to look at. And this one here, with you see the plus or minus, that's a dead giveaway that this is not well defined. H of 0 would be positive, would map to positive square root of 2 and negative square root of 2. So right there, basically every element, every domain value would map to 2 target values, right? One positive, one negative. That's not well defined. And they give you an example and stuff. Right. But every element of the domain has to map to exactly one element of the target for your function to be well defined. So pay attention to what your domain and your target are. Okay, then we talk about strings. Strings were brought up in the last chapter. The domain and target set for a function can also be a set of strings. Remember this 0, 1 to the third just meant all bit strings of length 3. So like 0, 0, 0, 1, 1, 1, stuff like that. And 0, 1 to the fourth here meant all the bit strings of length 4, 4-bit strings. So you can have functions, between sets of strings as well. So let's take a look at some examples. Now this one, again, I'll just write this out, and we'll take a look at it. So we have a function from the 2-bit strings to the 3-bit strings. And the rule is, remember, one operation on strings was called that concatenation, where I just add bits, onto strings and make them longer, or connect strings. So f of x, this function f is going to take a value, an element from the domain, a 2-bit string, and just put that 2-bit string down and throw a 1 in front of it. Concatenate, just add a 1 to the 2-bit string. So let me show you a mapping. So we have our domain, right? The set of 2-bit strings. Now there are only 4 2-bit strings. There's 0, 0, 0, 1, 1, 0, and 1, 1. And the target is the set of 3-bit strings. And there are 8 of these, and again, you've seen this, right? So I'll put down 8 dots. This isn't that big. And the 8 3-bit strings, you have 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, and 1, 1, 1. And here's the mapping, what this function f does. It takes an element from the domain and just simply adds a 1 to the front of that string. So 0, 0 maps to 1, 0, 0. It just throws the number 1 in front of that string. 0, 1 would just map to 1, 0, 1. So right there. 1, 0 would map to 1, 1, 0. There's 1, 1, 0. And 1, 1 would map to 1, 1, 1. Okay. There you go. And this is a well-defined function, right? Every domain element is mapped to exactly one target element. The range is just all these 4 3-bit strings here that start with 1. The range is 1, 0, 0, 1, 1, 0, 1, 0, 1, and 1, 1, 1, which is a proper subset of the target. Okay, now let's take a look. So very simply, what is f of 0, 1? I already said it. F of 0, 1 would be 1, 0, 1. It just throws 1 in front of the string. And I already mentioned the range as well. Just those 3-bit strings that start with the number 1. Okay. And the last part of this section, before the additional exercises, is on function equality. What does it mean for two functions to be equal? There's a couple things. Right? Two functions, f and g, are equal if f and g have the same domain and target, and f of x equals g of x for every element x in the domain. Right? So they have the same domain and target, and every element in the domain maps to the same thing for both functions. Right? F of x equals g of x for all x in the domain. Okay, so the question in these activities is, are these functions equal based on this definition of function equality? So according to each definition of functions f and g, is it true that f equals g? So this first one, I don't even have to look at the rules. F has domain real numbers, target real numbers. G has domain real numbers, target positive real numbers. The domains are the same, but the targets are not. So I'm not even going to look at the rules. That was the first part of the definition. They have the same domain and target. These do not have the same domain and target, so they are not considered equal. Yes, these rules may be the same rule, and they are, but they don't have the same domain and target. Both parts of this definition have to be satisfied. All right, now here, same domains, same targets, reals to reals, great. Is the square root of x squared the same all the time as the absolute value of x? And yes, you may recall this from an algebra class. The square root of a real number squared is equivalent to the absolute value of that real number. So these will give me the same output for every input. And they got the same domain, same target, so these are equal. And then lastly, alright, so this set X is just the set with elements 0, 1, and 2. Both F and G have the same domain and target. They're both X and X. So now, do I get the same outputs for every input? Alright, so when I plug in 0, F of 0 would be 0 minus 1 squared, that'd be 1. Same as G is 0, you get 1. F of 1 would be 0, so is G of 1. It's 0. F of 2 would be 1, so is G of 2. So they have the same domain and target, and they have the same outputs for all the domain inputs. So they are equal functions. Okay. And then you have your additional exercises. Right? Now, some of these are on assignment 5. Others are not. Right? I would still recommend that you do all of them just for extra practice, and you can view the solutions. Please try to work them out though before you look at the solutions. Try to figure them out on your own, and then use the solutions as a guide. As a check how you did. Because if you just copy solutions, and that's all you do, you're not going to learn anything. So that's it for section 4.1. Bunch of definitions, introduction to functions here. If you have any questions, let me know, of course, in Canvas, and hopefully this is a nice guide for you and when you go and work on some of these extra exercises. All right, and thank you very much for watching.